Hello everyone. Today we're going to look at our star clock, and we'll have to construct this and use it to answer the questions in our lab, telling time by the stars. So if you've already constructed your star clock, you can skip ahead. If you haven't, it doesn't really take too long. Let me show you how I'm going to go about doing this. Take my little skizzies and I'm going to cut this outer ring out first, and you can sort of take a look at it now if you haven't, and notice that in what we're going to call the outer ring has January through December, all throughout the year, months, and we got our inner ring, which has 24 hours of the day, or like our clock times. So all I did was cut this disc out. And now for this little guy here, I'm going to cut this out, which if you take a look here, you've got some instructions, which I'll go through with you in a second. You've got some common asterisms or constellations, if you will. Cassiopeia, the queen tied to a chair. Yes, I get that it looks a little bit more like a W, or she looks a little bit more like a W than a queen tied to a chair, but that's the story the ancients used. You've got the Little Dipper, part of Ursa Minor, and the Big Dipper, part of Ursa Major. So you've got this little window here where it says the time is, we want to snip, snip, snip that guy out. So now I got that. And this, notice that you've got a little white circle there, Polaris. They call it the North Star here. That's like the nickname, that's fine. You got the little black dot in the center there. So I'm gonna take my brass fastener, poke it through that one as best I can. Should have probably found a smaller brass fastener, huh? But it'll be okay. Then I'll take this little guys, whoop, stick it through like a so. Flip this bad boy over. Open up the legs. Booyah. Put my scissors back into a nice safe location. And we have constructed a star clock. So you may notice the inner wheel now spins or rotates, right? A common question that pops up. Let's say, as I'm making this, today's May the 7th. So I'll have a lot of kids that are like, all right, Cash, I'm trying to use this for May, and I need to look at 9 o'clock at night. May only lines up with 4 p.m., 3 p.m. Well, that's true, but that's not how you use it. I would want to go outside, and I need to know what month of the year it is. So if it was May, boop, I hold on to May. I face north, and then I look at the stars in the sky, see how they align or what they look like. And if I match this up, it'll tell me what time it is. So this is very similar to our star finder, and you could use it either way. You might remember I kind of mentioned this when we did the star finder, where I was saying, if you know what time it is, you could set this, go outside, find the stars. Or if you go outside, find the stars, match it up, you can figure out what time it is. So it works as like a star finder and also as a clock. This one, telling time by the stars, we basically just take the more, let's figure out what time it is by trying to match up the stars, but it could be used either way. So let's jump into it here. At this point, we would have discussed the background information. You can either read your own or pause here to read through that again. We've talked about the procedure for constructing the star clock. We just created that guy there, so we're moving right along. And I just gave you a quick rundown of how to use it. So we're just going to jump right into the discussion questions. And if you've got the need, like I said, you're welcome to pause, stop, rewind, do what you got to do. So here we're asked about which hemisphere of the Earth would this star clock be useful for? Explain. Well, this is kind of reaching back on our Unit 1 info. You might remember we said we're in the northern hemisphere. And there's the equator just splitting. This is supposed to be the Earth, by the way. Not a little Pokemon ball. But we've got, the northern hemisphere and the southern hemisphere. The equator separates those two. And if I am a viewer in the northern hemisphere, I can't see stars in the southern hemisphere. Because while this is a two-dimensional drawing, we know the Earth is three-dimensional, right? I can't see out and down and around and under, but I can see the stars that are in the northern hemisphere. So will that change with what latitude I'm at or what time of year it is? You betcha. But this would be good for the northern hemisphere because that's where we're positioned and where you'd have to be to see these stars. So what does the hole in the center of your star clock represent? Boop, boop, boop. Polaris. If you wanted to call it the North Star, that's fine. But that's what I was getting at here, is this is your brass fastener that represents Polaris. Which way should you turn your star clock's inner circle to simulate how time changes throughout the evening? Well, just if we look at this, and I go from 10 p.m. to 11 p.m. to midnight to 1 a.m. That's the way that the clock rolls. If you notice, I'm just kind of moving this, and that would be counterclockwise, or that's going to be the opposite that a clock moves, right? So this would mean that we're going to move things counterclockwise. If you had to explain why, well, we know that the Earth rotates, right? And it also revolves. But, if we've got our Earth, there's the axis at that 23.5 degree tilt, and it rotates counterclockwise. That's going to give us the apparent motion of stars throughout the night sky. So I could fill in this one here for you now, and I bet by this point some kids are like, Cash, you're just sketching little pictures here and just kind of talking about them. How am I supposed to fast forward to the end and pause and just write down your answers? Well, I'd like you to put these things in your own word. I'll be happy to help you out or give you some clarification, but I don't want you just copying this stuff down. So we're on to number 4. What else can this star clock tell us besides the time of day? Well, this is something that I touched on earlier, right? If I wanted to figure out what time it is at night, I could find my month, hold that at the top, face north, orientate myself north, match up the stars, and it would tell me the time of day. Well, if I've got access to a timepiece, could I set this for the time of month, set it for the time of night, face north, and then expect to see these stars here? Sure. So, again, you can use this as a clock, or you can use it as a star finder. Works either way. And the star finder that we made in Unit 1, could you use that both ways? Absolutely. You could use it to figure out what time it is if you match things up. And you could also use it to determine where your stars are located. So could you make an argument that this could also act as a map? Yes. I think you could say, look, I know where we're positioned in space if I know what these are at. I don't know if you didn't know that, though, how you just be able to figure it from this. So let's stick with it being a star clock and a star finder. So what causes the North Star to appear to remain in a fixed position in the sky? Goodness gracious, we've covered this in great detail, but it's okay. We'll take a look again, right? If there's the Earth, there's the axis, or that 23.5 degree tilt, and if you followed that out into space, you would run into Polaris. Neat. We have a pole star. The Earth rotates counterclockwise. All the other stars, we've seen like those time-lapse photos where you kind of get the smears that don't rise or set. They would be called circumpolar. We'd just follow them around or circle around the pole stars. Some would rise in the east and set in the west. They would take the same counterclockwise motion. They just wouldn't be circumpolar. So what causes the North Star to be a good directional star? It just happens to be located above the Earth's axis. So is this the way it's always going to be? Nope. I know we haven't talked too much about precession or the Earth's wobble, but over time, our axis is going to point in different directions in space. And as that occurs, we're going to lose Polaris as a pole star. And there'll be chunks of time where we don't have a pole star at all. As we speak, there is no like South Star. It's just random coincidence that we've got Polaris or the North Star located above our axis. This wobble to get back, it's about a 26,000 year process. So for our lifetime, we'll have Polaris as a good directional navigation star. Moving on, huh? So here I ask you about, describe why the stars appear to rise and set. Well, because the Earth rotates. The Earth rotates. I mean, right now, if you were to think about the room that you're in and you rotate, you're going to see different things in that room. Well, if you're on Earth and it rotates, you're going to see different things in space. So if you had to give an explanation that would help even an elementary school age student understand why that's happening, I would probably just have them rotate and describe what they're seeing. And rather than just having them spin as fast as they can and fall over, just maybe tell them to take like a quarter turn or a half turn, or just kind of like slowly position their shoulders in different directions and ask them, what do you see? What do you see now? What do you see now? Did the room move? No, you moved. So does that change your view of the room? Sure. Same thing happens as we're going to be riding around on spaceship Earth. As we rotate and revolve, we're going to get different views of the night sky, or we'll see different stars. So that brings us to number 7. If we had to compensate for daylight savings time, what would we have to do? Well, the same thing that we do with regular clocks, right? We've got our inner clock ring. You would just want to adjust an hour. And the little trick to keep that straight is, if it's in spring, you spring forward to set your clock. And in fall, you fall back to set your clock. As we're right now in May when I'm making this, though, we're starting to save some time. And, we wouldn't have to compensate for that. So what direction do stars appear to rise from? In which direction do stars appear to set in? They're going to rise in the east and set in the west. So if that's me, I usually wear a hat. So there you go. There's my little hat. And I like stars, so I'm happy. Anyways, if this is the west and this is the east, and we know that we're on spaceship Earth and it's rotating counterclockwise, that backwards motion. This one doesn't show us stars rise or set above or below the horizon. It just kind of shows us the direction that they're moving. But, we've made them with our star finder and seen simulations and discussed in lecture. What I would see is stars start to pop up, or if it's daytime, the sun starts to pop up in the east, make its way through the sky, and then they appear to set in the west. All that's due to the effect of Earth's rotation. So, excuse me, use the space below to draw where the Big Dipper can be found each season of the year. Well, I would just pick a given time here, and this will be one where I'll allow you to stop and pause to sketch. So, let's start with okay, I guess I'm in June, right? So at or around June 21st, that would be like summer. Now, do you have to start at summer? No, maybe you want to start at the vernal equinox, since that's going to be where, we've got our equivalent of a prime meridian on the celestial sphere. But, I'm looking forward to summer, so I'll go summer. And then I know if we're moving through the seasons, we go from summer to fall. If you want to call that autumn, that'd be fine. And then after fall, we go into winter. And then after winter, we start to see some spring. And then that process repeats, right? Because we are making our way around the sun, and that process repeats. So anyways, let's take a look at summer. I'm going to set this for, we'll say 11 p.m. So if I hold this up at the top and I were to face north at 11 p.m., I would see the Big Dipper on its bowl. That's oftentimes what we refer to that part as. So my little sketch is just going to look something like that. Is that the greatest sketch in the world? Heck no, but I never claimed to be much of an artist. So fall, same time at night. If I were to go out in, when do we say fall starts? Around my birthday, right? So that's going to be at or around September 21st. Whoop. Now, we want to see that at 11 p.m. in fall, the Big Dipper is going to have a different appearance. It's more, I'd call this upright. So if you want to pause, sketch that out in a shape like that, you can. So then we move into winter, starting at or around December 21st. Whoop, 11 p.m. I would now see that the Big Dipper is positioned like this. I would say that's like standing on its handle. So you'd want to sketch something along those lines. And then last but not least, we make our way back into spring. That happens at or around March 21st. Cash, it's still cold. It's not like spring in March. Well, these are locations in space and seasons that start. We're not just describing expected weather for different months. So anyways, I would now say that the Big Dipper is upside down. And you can pause, check that little guy out there, and sketch that out. So same stars, same time of night, but we would expect them to be at different spots and appearances in the sky. So that gets us to number 10. Is the Big Dipper a constellation? No. The Big Dipper is technically just part of another group of stars, Ursa Major, and that's technically an asterism. So if somebody said, well, explain to me why it's not a constellation, I would say technically a constellation is a region of space, and an asterism is a group of stars. Furthermore, the Big Dipper is actually part of a much larger group of stars, and that's referred to as Ursa Major, or the Big Bear. So, why are Polaris and the Big Dipper considered useful signposts in the night sky? Well, we've got the Big Dipper here, right? And we said that, if you can find those pointer stars, it's a good jumping off spot, right? So with this, we could follow the Big Dipper, those pointer stars, Altair and Deneb, find Polaris. That's in the handle of the Little Dipper, which is part of a larger group of stars, Ursa Minor, or the Little Bear. We could go back to the Big Dipper, follow the arc here. Remember, arc to Arcturus, and speed on to Spica. If we're at the right time of year, we could follow this down and smash Leo on the head. They're just good spots to just kind of jump around and find a lot of other stars. So that's usually referred to as like a signpost, just because it's kind of telling you where other things would be. With a little bit of knowledge, like what we've discussed throughout the class so far, if you can find the Big Dipper and then Polaris, you can jump around and find quite a few other things in the night sky. So how bright's Polaris? Compare that to other stars or planets that might be visible. Well, there's a common misconception that we've discussed, right? By now, you're probably like, goodness gracious, Cash, how many times are you going to tell me? Polaris, it's not even in the top 20 brightest stars as viewed from Earth. And I'd say, all right, repetition, that worked. Turns out Polaris is not really too particularly bright. It's just great for navigation because of that random coincidence that happens to be located above the Earth's axis. So our stars, how do they, or what direction do they appear to move around Polaris? Counterclockwise, because that's the direction that the Earth rotates. As viewed from space, the northern hemisphere, and again, I haven't touched on this in this lab, but we've discussed it, right? If I'm in a little spaceship and I'm up here, I guess my spaceship's just a little dot. That's okay. and I were to watch the Earth rotate from the northern hemisphere perspective, I would see it move counterclockwise. But now I take my little spaceship, boop, 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 beep, 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 and now I'm down here, and I'm watching the Earth rotate. From the southern hemisphere, underneath the Earth, looking up, it would actually give me a clockwise appearance. But we're not discounting the good people in the southern hemisphere. We just take a northern hemisphere perspective because that's where we live, about 42 degrees north in Dearborn Heights. So Polaris, it's actually part of what circumpolar constellation? Asterism would be more accurate, but I'm guilty of using those terms interchangeably. Apparently typing them interchangeably as well. Where can we find it in the constellation? Well, remember our brass fastener represents Polaris, and that's in the handle of the Little Dipper. Or if we had a more complete star map here, we would see that it's in the tail of Ursa Minor, the little bear. So hopefully that's shed some light on being able to use your star clock and how to construct it. And it's a good reminder that we can not only determine the time of day, but also the location of stars, all from one neat little contraption. You've got questions, concerns, please don't hesitate to reach out. Till we meet again, be safe.